right, AP Stats, let's go ahead and do a quick overview of everything that we've talked about with respect to experiments and observational studies, and then we'll look at your exit ticket problems. All right, so it's very important to not mix the language of experiments with the language of sample studies and other observational studies. They're two different things, right? Remember, the big difference between the two is random assignment of treatment. So random assignment of treatment is with experiments. Random sampling is typically with observational studies. And what I mean by that is that with experiments, we usually have to take volunteers. In an ideal world, random sampling would go with experiments as well, but with experiments, you can't randomly sample the population and tell them they must participate in your experiment. We're not all like Dr. Frankenstein over here. So typically, random sampling goes with observational studies, and then random assignment with experiments. And we'll talk more about that in Packet 5, our last packet with this unit. All right, random sampling overview. When do we use it? So we use it to select a random sample for our survey. So we're selecting the people that we're going to survey. Compare that to random assignment. The people have already been selected. We already have our sample. So we already have the sample size. We use random assignment to assign treatment. And again, that goes with the difference between experiments and observational studies. With observational studies, we're just observing. We're asking them what they think about something or observing past or present data. With experiments, we're actually randomly assigning the treatment. All right, why do we use it? We use random sampling to be able to generalize conclusions to a specific population. So we need to be able to generalize, so that has to do with like the selection bias, right? If we don't randomly sample, we fall prey to sample bias, right? Selection bias. So we need to be, sample bias and selection bias are essentially names for the same thing. So we need to be able to generalize conclusions about our findings back to our population, and we can't do that unless our sample was random. Why do we use random assignment here? Well, number one, that's what defines an experiment. And number two, to draw conclusions about cause and effect. So we can say that if we do all this right and have random assignment, we can say that the explanatory variable causes the response variable. Causes the change in the response variable. All right, so with random sampling, we had 4 different types of good random samples. Can you think of them? Put them in right now in that Edpuzzle question. All right, I hope you said simple random sample, stratified random sample, okay, I literally can't spell random. That's how fried my brain is. Stratified random sample, cluster sample, and systematic random sample. Good morning. So all of these are random samples. They just do the random selection in different parts of the sampling process. So with simple random sample, everyone in the population is equally likely to be selected. Everyone has the same chance of being selected. Remember, with stratified and cluster, we create groups, but the randomness happens in different parts. With stratified, the different groups are the strata, and we randomly select from each group. And that's if we want our population to have the same amount of a certain group. Like if we're sampling the student body and we want to have the same amount of freshmen, sophomore, junior, and seniors, we would do a stratified random sample. So we randomly select from each strata. With cluster sampling, we randomly select the cluster and then survey everyone in the cluster. Now, cluster sampling is mainly done for convenience purposes, to be able to save money and make the survey quick. And we're still doing random selection by randomly selecting the cluster, right? So we can still generalize back to the population that we're surveying. It's just definitely a different way that's done for convenience. All right, and then systematic random sample is where we have the list of the population. We pick a random starting point. And survey the nth person. So every 10th person after that, that's who we would pick. That's systematic random sampling. So those are our 4 random sampling methods that we would use to be able to generalize back to a population. All right, random assignment. We have 3 different ways that we talked about today, actually, of doing random assignment. We could have completely randomized design. We could have randomized block. And then we could have matched pairs. And I won't go into detail of those because we just literally talked about them today. Remember, completely randomized is where everyone in your sample has equal likelihood of being assigned one treatment or the other. Randomized block is where you put them into blocks first to eliminate variation in your results, right? Eliminate variation. So you could put them into different blocks, and then within each block you assign the treatment randomly. And then matched pairs is where you match up all of the samples into pairs of 2, and then you could give one of the pairs one treatment and the other one the next. Remember, the random assignment is happening within the pair matching, right? So you'd flip a coin within the pairs to see who gets the treatment number 1 and who gets the treatment number 2. All right, let's go over these 4 problems and then we are done. All right, AP practice problem number 1. In designing an experiment, blocking is used. So remember, randomized blocking is one of our random methods of assignment, right? So let's see our answer choices. Reduce bias, reduce variation. As a substitute for a control group, let's go ahead and eliminate this because we know that we have to have a control group for comparison, right? That's one of our 4 pillars of experiments. As a first step in randomization, well, it could be a first step, but it's not necessarily always the first step, right? You could have a completely randomized design where we don't need any blocks. So it's not always used as the first step, so let's eliminate that. And then to control the level of the experiment, we haven't talked about levels and blocking together, so that's definitely out of the question. Okay, so bias would mean that our answers have some sort of skewness in them that makes them inaccurate. Bias means our answers are inaccurate. Variation does not indicate inaccuracy, but it does say that your answers are pretty spread out, so it's difficult to tell where the true mean or the true variation means spread out. And ideally, we would not want our results to be pretty spread out because then it's hard to see what the true answer is, right? So blocking is not necessary to have accurate results. So it's not there to reduce bias. If it were there to reduce bias, we would have to block every time because we don't want bias. It's there to reduce variation. Bias means our results are inaccurate, and if we're not blocking, that doesn't necessarily mean our results are inaccurate. Okay, so reduce variation is the first one. Practice problem number 2. Which of the following is not important in the design of experiments? Okay, so that's a blast from the past, and by past I mean 2 days ago. So remember the big 4 things of an experiment: comparison, random assignment, control of lurking variables or confounding variables, and replication. So which of the following is not important? All right, well, control is number 3, control, so that is important. We'll eliminate that. Randomization and assigning subjects to different treatments, that's number 2. Let's eliminate that. C, replication using sufficient numbers of subjects, that's number 4. Eliminate that. Care and observing without imposing change. Well, wait a minute, that doesn't sound like an experiment. We definitely impose stuff in experiments. So D could be our answer. Let's eliminate E. Isolating variability due to difference between blocks. That could be possible, right? That could be important. So D is our answer. All right, practice problem number 3. Good morning. How are you?
Good.
Which of the following is a true statement about the design of matched pair experiments? All right, I thought this one was definitely the hardest problem. All right, so we want a true statement. So most of these statements are probably not true. All right, each subject might receive both treatments. Well, actually, I think that's probably true. Remember we talked about the Coke Pepsi taste test? That would mean that each subject takes both the Coke and the Pepsi just in different orders. So A is probably our answer, but let's eliminate the others. Each pair of subjects receives identical treatment and their differences are noted? No, in a traditional matched pair design, you have a pair of people, one gets one treatment, the other gets the other treatment. They don't get identical treatment. All right, and A is different than B because A says each individual subject, meaning the matched pair is actually just one person, and you're a matched pair with yourself taking both treatments. Here, if you have 2 subjects, they're not going to get identical treatment. All right, blocking is one form of matched pair design. It's actually the other way around. Matched pair design is a form of blocking. So, like, I wouldn't say that that dogs are one form of poodles. I would say poodles are one form of dogs, right? I have a poodle Spencer. Poodles are a form of a dog. So dog is the big category, and poodle is the specific breed in that category. So blocking is the big category, and matched pair design is one form of blocking. So it'd have to be the other way around for this to be true. D, stratification into 2 equal-sized strata. All right, in your mind, you should be being like, what? Stratification? That doesn't have anything to do with matched pair. Remember, stratification is random sampling in observational studies. So stratification is not part of experimental design. Eliminate it. And then, oh my gosh, this hurts my eyes to see. Randomization is unnecessary. Oh my God, no. No. Randomization is always necessary. It's one of our big 4 pillars, number 2. All right, so A was our answer here. All right, the last one. Some researchers believe that too much iron in the blood can raise the level of cholesterol. The iron level in the blood can be lowered by making periodic blood donations. A study is performed by randomly selecting half a group of volunteers. So I got the volunteers, and I'm randomly selecting half of them to give blood donations while the rest don't. Is this an experiment or an observational study? All right, so the word randomly selecting is throwing me off because normally I see random assignment, right? But this is actually random assignment hidden as random selection. They tried to trick you by not using the word assignment, but if you take a step back and look at the big picture, you'll see that we have a group of volunteers and we're imposing treatment. We're saying, hey, you need to give blood donations while the rest of you don't. If we're going in and we're telling people what to do and we're being bossy, we're experimenters. So this is an experiment, not an observational study. If it was an observational study, we'd kick back and be like, we don't care what you do as long as you tell us. So this is an experiment, so we can eliminate D and E. All right, so is it an experiment with a single factor? Is it an experiment with control group and blinding? Or is it an experiment with blocking? All right, so far, I think the most correct answer is A, because we do have only one factor, whether or not you get blood donations. So I'm going to tentatively circle A, but let's eliminate B and C. So an experiment with a control group, it definitely has a control group, right? Half of the group doesn't give the blood donations. And blinding, what is blinding again? That means where the people don't know whether or not they're getting the treatment. I don't think we can have blinding with blood donations. I think if you're getting a needle shot into your arm, you know that you're getting the blood donation, so there's no possible way to do blinding. So B is eliminated. And then C, an experiment with blocking. Blocking would be where I took the entire group and I divided them into group number 1 and group number 2. And then within those groups, I say, group 1A, you get your blood drawn. Group 1B, you don't. Number 2, group 2A, you get your blood drawn. Group 2B, you don't. So I haven't done that. I haven't blocked into 2 groups and then randomly assigned treatment. All I did was take my first big group and split them up. So there is no blocking here. The answer is A, an experiment with a single factor. All right, one more packet down and we are done with this unit.